Good morning. We wait for a couple of minutes. No. No. Okay.
As you wish, as you wish.
Con la venia de. Okay. Good morning, everybody, and welcome to this second session morning. And it's a pleasure to me to introduce Professor Roman GER as the first speaker. And he's from Silesian University, Katowice, Poland. And the title of his talk is Convexity and Difference Property. So,
Okay, thank you, Mr. Chairman. Ladies and gentlemen, good morning. The previous session was generally more or less devoted to the generalized monotonicity, and at least with my talk, we come back to convexity, and even not generalized, I would say the classical one, again, more or less. Let me start with definition of recalling the definition, because I am absolutely convinced that everybody is familiar with the notion of the difference operator, which looks like this. Assume that we are given clearly a non-empty family of functions mapping R into itself, and let it be script f, and assume that the difference operator is defined here. And assume that we are in such a situation that for any arbitrarily fixed age from R, the operator delta h applied on a function f falls into the class, prescribed class capital, prescribed f. And we say, after, and Dutch mathematician N.G. de Bruijn, last year there was a conference in Leiden in Holland devoted to celebrate 100th anniversary of his born. And he defined the difference property in the following way, that if this, excuse me, that's not what I wanted to have. If this difference for each age falls into the given class f, then the function itself, the function f itself, admits a representation of the sum of a function from the given class and an additive function. Clearly, in general, this is more or less a wishful thinking to have this. But once we really have it, we say that the given class of mappings possesses the difference property. And de Bruijn himself, in his fundamental paper 3, I will share the references at the end of the talk, but remember 3 was the basic, the fundamental paper of de Bruijn. He has shown that the following function classes, which are listed here in green, actually do have the difference property if it sense, and that is, let me repeat, the class of continuous functions, of functions that are k times differentiable, doesn't matter what is k, ck functions, analytic functions, functions which are absolutely continuous in any compact interval, and functions with bounded variation over any compact interval. So pretty long list of classes, of important classes of functions, and all of them have the difference property, and actually in some cases it's not that easy to prove it, but he did it. And so having this list in mind, we can ask whether we have an example of a class of functions which does not have the difference property. Actually, there is such a class, important one, the class of all Lebesgue measurable functions on the real line, unfortunately, misses to have this property. And this was also realized by De Bruyne. So you see, I am using the colors in green in the positive case, in red in the negative case. Right? So the class of all measurable functions, as you see, fails to have the difference property. And then people were working on it in some more general setting, for instance, on abelian locally compact groups. The essential results of F.W. Carroll and F.S. Curl touch this thing. And you see, Riemann integrable functions on the real line also have this property, the difference property. However, in this fundamental paper 3 of De Bruyne, it was not listed. It was only announced that he was working on it but was unable to decide it. Some 2 years later, he decided it in positive. So again, Riemann integrable functions have the difference property. And you have here Riemann integrable functions on locally compact group. What does it mean? It means simply, we say that the function of such a group is Riemann integrable, provided that the set of discontinuity points of such a function has Haar measure 0 in that. Let's say on the real line, everybody knows it's equivalent to Riemann integrability. So in this case, it may serve as a definition. And maybe it's worth it to mention that these investigations were there generalized to higher order differences. That is, we simply iterate the delta H operator and having this, to say, for some reason it would be good to put it n+1 H F, which is just the n+1 iterate of the operator, and this for any H, say in R for simplicity, belongs to the class F, then the expectation is that F itself can be represented like G plus P, where this is the function G satisfies the inequality like this. It was already told in the talk of Professor Zsolt Pales, also I believe Attila Gilani, convexity of higher order, of nth order in this case. And P, you remember in the classical case of De Bruyne, the other term was simply an additive function. And in this case, P is assumed to be polynomial function, that is, this vanishes identically with respect to H and the argument of F. And once we have this, we will say, if the answer to that question is in positive, then we will call it the function, the class of function script F to have the difference property of order n. And for many classes of classical functions, classical function spaces, it was proved again in positive that they have this property. The main results are obtained by, unfortunately, past Zbigniew Gajda, a PhD student of mine who did it But I will not speak anymore about the end order, only going back to the first, to n equal to 1. Actually, what is perhaps, at least for me, it was a bit surprising that people, including De Bruyne himself, didn't care or didn't look for the important class of convex functions, whether or not they have the difference property. It turns out that I didn't find in the literature any result of this kind, neither in positive nor in negative. But it turns out that, unfortunately, as I wrote it here, also that problem looks very natural at first glance. It happens to be slightly vapid. Why? The proposition explains it. Namely, the situation is like this. If the difference operator for any age applied for any convex function f for any function f from the given class falls into the class of convex functions, then in positive case the expectation would be that the function itself can be split into two terms. The first is just convex and the other is additive. Unfortunately, it's not true. So formally speaking, the class of convex functions fails to have a difference property. But we can say much more. What a proposition says, namely, if we have one, relationship 1, then the function itself has to be of this form, this one, that is some simple quadratic function plus an additive one. And this quadratic term here is actually convex if alpha is positive. But if alpha is negative, it is concave. So you see, it, in general, this class fails to have the difference property. But with the aid of this proposition, we are now familiar what's really the situation with the class of convex functions with this respect, right? So this is generally described. And of course, conversely, each function of that form satisfies condition 1, so you can check it even without any writings, okay? So this is more or less decided. If you like, the proof is not very complicated. Maybe 1 minute will be just to show it how. The essential observation is that we have this equality for the difference operator, and if it is supposed to be convex for every age, then you see it's also convex for minus h, but this is minus before the operator, so actually we have equality. And once we have equality, that means the function itself, the delta h itself, is an affine function, because it is simultaneously convex and concave, right? If it is affine, that it must be of that form, C of h, because clearly this affine function depends, for singular h, depends on h. So it looks like this. And after some simple substitution, you come to formula number 2, which is, look at the left-hand side, this is symmetric with respect to h and x. And you use this, then you get that this has to be valid. And if you divide it, then you get immediately that this quotient is constant. And that's practically the end of the proof, right? So you see, it's not difficult to show it. This observation was an essential one. By the way, you see, in this problem, not to have, as I called it, the difference property question not to be vapid, you should assume probably, I'm absolutely convinced that we should, to assume it only for positive age. So this would disappear, this thing, beg your pardon. I pressed on the wrong button, okay. Oh, let's go back here. And if it is valid for all age, positive and negative, as De Bruyne wishes to have, then we have this triviality. And if we would assume it for only positive age, then the problem becomes much more interesting and not yet solved by me, but I believe I will succeed to do it. Anyhow, this would be a modification of the definition of the difference property, because we would assume this appartenance not to be valid for all age, but only for positive age, right? But the problem now becomes, for convex function, becomes much more interesting, and at least for me, not yet solved. And let's go back here. A simple observation numbered star here is that if we have a function which is already represented as a sum of a convex function and an additive one, that is what we would like to have, such a representation. It still doesn't go back, because if we calculate the difference operator on this, you get things like that. This is okay, but this is not. Because if H is negative, then this is not convex, right? So you see that it's a second reason to deal with positive increments only in the case of convex functions. You know, that's this observation. Okay. So if we don't have what we like, we have to like what we have. Actually, the good behavior, and that's the main result I would like to share with you, of mine, that we switch into the class of so-called delta convex functions. What are delta convex functions? On the real line, the definition is very easy. A function is called delta convex if and only if it's a difference of two convex functions. And this is very reasonable definition, because it refers to, say, bounded variation. Bounded variation more or less means that the function can be represented as a difference of two monotonic functions, and look for it as a difference of two convex functions, that is delta convex. You can also think about differences of two functions that are convex of higher order, right, like with delta n plus 1 operator. And this is also treated and examined by me, but I will not bother you with this in this talk, but this is solved also for such type. Let's concentrate on delta C class of delta convex functions. And another good reason to deal with such a class of function is that the delta convex function, this family, is the span of the cone of convex functions, right? Linear span of that. So it's another reason to deal with this. And many very known mathematicians like Alexandrov, for instance, and his school, they were between the wars last century, they were very much involved in investigating this family. And my main result simply states that in this case, the family of delta C, of all delta convex functions, we have the difference property. Actually, the proof is not short. I would not bother with it. It takes time. Instead, I would propose that I will indicate only on some essential tools which I was using to get this proof, right? So the statement of the theorem is like here, that if for any h in R, this delta h operator falls into the class of delta convex functions, then we have this representation required as the sum of a delta convex function and an additive one. And conversely, each sum of this sort satisfies condition 4. So it's described, fine, it's closed. By the way, let me for a moment go back to this representation G plus H. In this case, we have G to be delta convex function, but in the previous case, we were thinking about simply convex function. And we have observed that generally it fails to have the difference property. Anyhow, again referring to the talk of Professor Zsolt Pales, this is a very important class of functions, namely right convex functions. That this is not the definition, but by the representation theorem Pales was talking about, that can be represented as a sum of a convex functions and an additive one, right? So such sums do not have the difference property, and such sums of the same shape, but with G being delta convex, does have the difference property. And now going back to these announced tools, let me talk a few words about so-called Q differentiability. This is essential tool I was using in my proof, and this goes back to 2006, the paper of Zoltán Boros and Zsolt Pales, paper number 2, where they have introduced this notion and observed some essential facts about such regularity behavior. And the definition is just here. You see, it is nothing else but the directional derivative of a function in the direction u, but the essential difference is that the coefficients here, this one, are allowed to be only rational. Actually, to be loyal, in Boros-Pales paper, they were considering arbitrary subfield of R. But for my purposes, Q will be the essential thing, the field of rational. And if this limit exists and is finite, then we will say that f is Q differentiable at the point x in the direction u. And if it happens for every x, then we will simply say that f is Q differentiable in its domain. And in very interesting things, which I listed here under the title Some Facts, the first thing is that each Jensen convex function is everywhere Q differentiable. Well, it is impressive actually, because Jensen convex functions can be non-measurable in the sense of Lebesgue, but they are differentiable in this sense. That is, all these facts were established in the paper of Boros and Pales. And the other good thing, clearly, additive functions are special cases of Jensen-convex functions, so they are also differentiable, also they can also be very irregular. And the derivative at the direction, in the direction u is simply the value of a at additive function at u. And dq operator is simply linear, as it should be, and what is in the proof of my theorem important, that concerning the, another thing, if f is differentiable in the classical, in the usual sense, then of course the two notions coincide, so it must be so, right? And if it is only differentiable from one side, then we have the two equalities like this. But this is valid only for positive u, positive directions, the other one for negative directions, right? Okay, and that's the one tool. I am differentiating functions which are potentially very irregular with the machinery of Zoltán Boros and excuse me, Boros and Pales. And the other thing is maybe a bit funny. Everybody knows that if we have an increasing continuous function, for simplicity say from R into R, then this antiderivative function given by this formula is a convex function, right? But what I said, this is not funny. This is known for first year students. But what is funny for me is that it is not so obvious and it's not so easy to find in the literature what is happening in the case this I here is only increasing and it can have the numerable number of discontinuities, right? Does such a formula define a convex function? Well, it does. It does. After some time, I finally found it in the book of Robert and Warburg, convex functions. I think everybody knows it. But the proof is 1.5 pages for this. And you have the lemma here, which is just, well, with 3 lines, like this. I will not read it. But why I could obtain such a short proof of this? Because in contrast to what Roberts and Warburg are doing, I am using only Jensen convexity. I'm checking only Jensen convexity. So C of x plus y over 2 is less or equal Cx plus Cy over 2. But given function C with this formula, we see that it is continuous, and when it is continuous, that it is convex in the usual sense, and that shortens essentially the proof. So this is the other thing, and my time is slowly to be over, so some comments only. The first thing, all these considerations were taken on the whole real line. With some technical corrections, but not very difficult, you can switch to an open interval as well. The other remark is, which I already said, remark number 2, that for convexity, it is really required to assume the original condition to be valid only for positive increments. That's the other thing. Remark number 3, replacing R by, say, Banach spaces, it is able. Such things were examined by me. What is happening? Actually, fortunately, the Q differentiability machinery works also in this case, so it is fine. What doesn't work in general is that I am using that certain function classes have difference property, De Bruyn's type results, but they were only on the real line. And now if I want to switch to such more general setting, I have to overcome that difficulty. And in many instances, using, for instance, Carroll's theorem, I can do that. I see that our chairman is being anxious, so oh yes, absolutely. Thank you for your indication. Yes. So the essential paper number 3 is of the De Bruyn, and item number 2, the paper of Borosh and Polish. The other maybe are of interest, but more or less I was talking about them. Robert Zwarberg is here. And Vesely Zajiček, let me draw your attention to the last item. Allow me to deal with delta convexity for vector-valued functions, but this is another story. Maybe next time I can say about it. I'm very grateful for your kind attention. Thank you.